So here we go. Welcome back to the second part of the lecture. Having talked about the basic block diagrams of a digital communication system, we call them transformation blocks. Now we need to a little bit understand what these blocks are exactly. I mean, what functionalities you can do within the block. For example, the first block, formatting. In formatting, you can do character coding, sampling, quantization, pulse code modulation. And we will talk about this during this course. I know we gave a brief introduction about it in the previous semester in the course of Introduction to Telecommunication, but this digital communication and this basic process in digital communication, one of the most fundamental ones, so we need to have a look at it and understand it very deeply. After that, we have source coding. Within the source coding block, what do? You have predictive coding, block coding, variable length coding, analysis coding, lossless compression, lossy compression. This is with all of these under the umbrella of source coding. And I told you, if you go to Google and search source coding, you will find hundreds of books on this topic. For this block alone, you need a dedicated course for it to master it. So we are just scratching the surface, knowledge the basics of each block, so that we can get started and understand. And for more readings, to be expert in any of these blocks, you need to read more. So see in which block you are interested the most, and go and search and read and understand, so that your project can be related to one of these topics or blocks. After that, we have baseband signaling. Baseband signaling is about waveforms, line code representation, return to zero, non-return to zero, phase encoded, multi-level binary, pulse amplitude modulation, pulse position modulation, pulse differential modulation, all these kind of topics and within this block. The other block, which is extremely important in digital communication system, we call it equalization. Why do we need equalization? We need equalization to remove the effect of the impairments that the channel cause to our signal. Yes, you have noise, you have fading, dispersion, distortion, all of them distort your signal. So how to remove all of these effects and regenerate your original signal, the direct one you sent at the transmitter, if you remember from the first slide. We need equalization. So equalization, if someone asks you what's equalization, removing the bad effect of the channel on my data signal. In any language you can define it, but you should understand that this is something to remove the bad impairments. Techniques on equalization are maximum likelihood sequence estimation, zero forcing, equalization with filter, adaptive filter, many techniques. We are going to study some of them during this course. After that, we have band pass signals. This is after modulation. This is after multiplying with the high frequency sinusoidal signal. What do we have here? We have coherent modulation, non-coherent modulation. What's the key difference between coherent and non-coherent? In non-coherent, you have low complexity, but not very good performance. In coherent, it's too complex, the receiver is very complex, but your quality is very good. There is a trade-off between them. If your application requires low complexity, you should go with non-coherent. If it requires high performance, you should go with coherent. So example of coherent modulation schemes, we have phase shift keying, frequency shift keying, amplitude shift keying, continuous phase modulation, and so on and so forth, and hybrid of these. Non-coherent, anything with differential phase shift keying. Also amplitude shift keying is non-coherent, frequency shift keying, continuous phase modulation, and hybrid of these. After that, we have waveform. We have orthogonal waveform, non-orthogonal waveform, M-array signaling, and too many types of these waveforms. that you select according to your requirements and according to the channel behavior. You have channel coding also. You have many types of channel coding: block coding, convolutional coding, turbo coding, polar coding, and many coding techniques. For example, the most recent coding technique that was proposed for 5G is polar coding. Which country produced this technique? Turkey. Which university? Belgian university. They were able to produce a new coding to the world, to Huawei, to Ericsson. This technique will be implemented in each and every future smartphone, polar coding. So it's possible that you can produce something from here and go internationally. It's not impossible. Now we have also, after that, we have synchronization. You need to synchronize. While you are transmitting your data, you transmit data, but also you transmit some non-data sequences just to make the synchronization. You need to synchronize with the data bar. If you are not synchronized with the data bar, you will be decoding something which is not data, and you will end up being decoding wrongly, I mean. For example, you have frequency synchronization, phase synchronization, symbol synchronization, frame synchronization, network synchronization. All these are synchronization issues. You have, see, the guy who asked me what's the difference between multiplexing and multiple access. And I told him they are almost the same, but they are implemented at different layers, at different levels of your digital communication system. One is implemented at the bit level and the other is implemented at the waveform level. And that's why each one brings its own its own challenges, its own design parameters. For example, multiplexing is usually implemented at bit level, and you need to multiplex different streams coming from different applications or different services or different users, whatever. But multiple access is usually associated with multiple users who are trying to access the channel, and we need to share this channel fairly with everybody so that everybody can get the opportunity to transmit his data. Otherwise, how would we communicate? We have, after that, spreading. We have direct sequence spreading, we have frequency hopping spreading, we have time hopping, and hybrid of these. For example, Wi-Fi uses SSS frequency spreading spectrum. And GSM also uses some of these. We are, for example, 3G uses direct sequence spreading. GSM uses frequency hopping, and there are some other systems use time hopping, and some other systems use all of them or hybrid of them to make your system more robust. You have encryption at the end. Encryption is a domain by itself. It's security. When you go there, you don't come back. Huge. We just talked a little bit about it because it's part of our communication. Why we need it? We can still communicate without encryption, but our communication will not be secure. Anybody receives our data, receives our signal, can get our data. Bad, so bad. We don't want this to happen. We must avoid it. Yes? Clear? Now, let's a little bit talk about the different types of modulation and remind you of the types of modulation that you have studied in the previous semester and see how are they going to be related to the modulation schemes that we will talk about them in this semester. For example, in the previous semester we studied the left side part of this diagram. Yes, we studied these. Do you remember with me? We started with amplitude modulation, double sideband, single sideband, suppressed carrier, non-suppressed carrier, vestigial sideband, frequency modulation, phase modulation, and we said in all these modulation we are using analog. We are continuously changing the amplitude level of the sinusoidal carrier according to the information signal. We are continuously and instantly changing the frequency or phase of the sinusoidal according to the message signal. That can be also sine or rect or whatever. Yes. This means that you have infinity number of values, infinity number of points, whether in frequency or phase or if I give you here, let's tell you, let's draw a signal and see, for example, this is sine, and I tell you, for example, how many values you can generate or take between this point and this point, between, for example, 0 and pi over 2. How many points you can get here? You can get here infinity number of points. But in digital, you have points, only points. Yes? Finite number of points. That's why it's really different game, different system. And that's why this system is more robust to errors than analog systems. So we know this very well. Yes, you remember it? I asked about it at the exam many times. We are now moving to here. And not even to here, but also to other techniques as well. So here we start with pulse modulation, and pulse modulation can be divided into digital modulation and analog modulation. Digital modulation we go to pulse code modulation, PCM, and analog modulation includes pulse amplitude modulation, pulse duration modulation, pulse position modulation. Pulse position modulation, you just change the position, the index of your pulse according to the incoming information. In pulse duration modulation, you change the width, the interval, according. In pulse amplitude, you change the amplitude level to a discrete value. To a discrete value, you change it, not to an infinite number of values like continuous wave modulation. Clear? So these are the different types of modulation that we are interested in and we usually use. Again, this is another type of classification, but here I just drew, like, assume you have a sinusoidal signal, and the pulse amplitude modulation, the resulting signal after you do pulse amplitude modulation is something like this. You just take discrete values of the amplitude so that this signal can be carried over here, or you can detect, you can know that this is this signal by connecting these columns with each other. And here, pulse duration modulation, you change the duration of the pulse, you see, according to the incoming information. When the amplitude increases, you increase the width. When the amplitude decreases, you decrease the width. And this is pulse position modulation, and this is PCM modulation. These are the resulting signals. We will later, during the course, we will understand exactly how we can generate them and produce these types of signals from the data we want to transmit. So the first step in digital, in moving from analog to digital, is analog to digital conversion, because we have the signal in analog usually and we need to convert it to digital. What do you do to achieve this? What are the three basic principal steps that we need to perform in order to take a signal from analog and convert it to digital? These steps include sampling, then quantization, then encoding. Sampling, what I mean by sampling? Basically, without confining ourselves with a textbook definition, You have any signal has the x-axis, which represents the time, and the y-axis, which represents the amplitude of the signal or the power. Sampling deals with with the time axis. Instead of taking infinite number of values, instead of taking all the values on the x-axis, on the time axis, you just take points. Yes, points in the x, and these points we call them samples. You take the value of the signal corresponding to that sample in time, and these should be placed wisely so that you can reconstruct your signal at the receiver after you transmit it. And what was the condition to do that? The sampling frequency should be greater than or equal to the maximum frequency spectrum of your message multiplied by 2 to be able to, in order to avoid interference between the transmitted pulses. This is sampling. Quantization, you go to the y-axis. Instead of taking infinite number of values, you take only discrete number of values, finite set of discrete values. And that will reduce the amount of values you will need to transmit. So, in sampling, we convert continuous time to discrete time. In quantization, we convert continuous amplitude to discrete amplitude at certain points. And after that, we can do encoding. Encoding, each level, you can map it to a certain binary sequence. And then you collect all these sequences together, and you say that this sequence represents that analog signal. Now you can deal with this sequence and process it using your digital algorithm, using your computer, using the resources you have, which is really turns out to be very useful, because we cannot process analog signal. We need to deal with bits. We need to deal with something that the computer understands. Computer only understands zeros and ones. Yes? We don't have computers that understand analog. Anybody knows any computer that understands analog? We don't. We just have the language of the computer, zeros and ones. So quantization, therefore, is the process of converting continuous amplitude samples, as we said, and we denote that by M, where M is the message, denote the message, and TS is the sampling time, which is equal to 1 over Fs, the sampling frequency, and N is the index of the sample, 1, 2, 3, 4, 5, 6, 7. Of a continuous message signal M of t, at time t equal NTS into a discrete amplitude, and this is what we briefly discussed about in the previous course a little bit. But this is basic. This is the turning point between analog and digital. This is where we go to digital. That's why we need to refresh our memory with it, understand it, give more time to comprehend it, and so that we build solid foundation for it. This process is illustrated graphically in the next slide. For example, let's take a look at the quantization process. What do you have here? Can you explain to me what do you have here? You have a signal that looks like sinusoidal signal, but it's not. And as you can see, there are samples that are taken from this signal at certain instances of time, and these samples they are corresponding to actual values of the signal, message signal. For example, at this point of time, you have value 1.3. Yes, the natural sample value here in this line, the actual value of the signal. At this point, you have 3.6. At this point, you have 2.3. These are, you take them, you just map at the sampling point, map to the signal, and you just take the value. But after quantization, I don't have all of these values. I have finite set of values, and I need to approximate the actual value to one of these quantized values, because this is how it works. And due to this approximation, I will end up getting some quantization noise, some inaccuracies. Yes, because I'm not taking the actual value. For example, here, when I take 1.3, I don't have, when I go here to the quantized values, I don't have 1.3. I have only, what do I have? 1.3, I have the closest two values, 1.5 and 0.5. Which one is closest to 1.3? Definitely 1.5. That's why 1.3 is treated as if it is 1.5. The code number, after you put the code number 0, 1, 2, 3, 4, and it corresponds to code number 5, which is in binary 101. You take the next sample, this sample, you see its actual value. What's the actual value? It's 3.6. This value is exactly 3.6. Do we have 3.6 in the quantized values? We don't. What's the closest value? 3.5. Take 3.5. 3.5. What's the code number of 3.5? 7. As you can see here, it's the law here corresponding to 7. 7, how do you represent 7 in binary? 111. So you end up, after you do all this, after you do the same process to all the points, you end up getting this binary sequence. And this we call it BCM sequence, pulse code modulation sequence. This is a sequence of zeros and ones that represents this message. So if I give you this message, this shape of a message, you can get this. And also, if I give you this message, you should be able to get this. The transmitter, I give him this, produces this. The receiver, I give him the sequence of bits and it produces the signal. The reverse, just go the reverse process. That's the basic concept of quantization. Is it clear? Any question? Very important concept, very critical. This is the turning point between analog and digital. So we should understand it very well. And I think this figure is very clear, it explains itself. So, having talked about quantization, defined what's a quantization, sampling, and how do we quantize a signal, the natural value and this and that, we agree that the quantization, usually we perform it uniformly, but uniform quantization is not always the optimal one, because sometimes if you remember, like when you talk loudly, you have peaks, but when you talk like with low voice, you don't have too much peaks. Now, if your step size, the quantization size, the difference between the quantized level is fixed, and you are going to use it for any situation, in this case, if you are talking loudly, you would need too many digital steps, and these will not bring any difference to you. Also, if you are talking like with a very low voice, then the delta might be larger than the changes of your low tone, and it might not capture the details of your voice. That's why we need to make our quantizer sometimes non-uniform. Non-uniform is just like adaptive that changes the delta according to the changes of the signal. I adjust my delta so that I can always capture the details of my signal without sacrificing the performance. The step size is equally spaced in uniform, while in non-uniform the step size is changeable and variable to the sample amplitude. Clear? Uniform and non-uniform. We have uniform quantization, which is the simplest one, most popular, and we have two types of it. Quantizer can be classified into staircase-like or nonlinear, and we have mid-treed and mid-rise. the key difference between mid-read and mid-rise is the fact that in mid-rise, we don't take the zero level as a quantized value. The quantized value should be around zero. If in mid-read, we take the zero level here as one of the quantized value. This is the key difference between them. So in the question, I may ask mid-read or mid-rise, quantize according to mid-read or mid-rise. What do you do? If it is mid-rise, you just go away from the zero, divide the step size delta around the zero value. Like if your delta is 4, you go above 0.2 and below 0.2. And you build on top of that. Then 2, 6, 10, 14, and so on and so forth. If I said mid-read, you must start from 0. 0, 4, 8, 12, so on and so forth. Now, each one has produces different result actually, totally different result. So you need to be aware of that, and you need to consider it and pay attention to it. For example, design a quantizer circuit to quantize the following sequence of samples using a mid-read quantizer. Mid-read quantizer, you need to go away from the zero. You cannot start mid-read. Actually, this is mid-rise. Yeah, these points are the quantized ones. The red points are the quantized values. And this is the zero level. Since we are going away from the zero, this is mid-rise. So mid-rise is this. So according to this, we have this sequence, these values. These are the amplitude values at certain points of time. And I'm just saying, as if I'm saying, approximate them to the closest quantized values. So first thing you need to find delta. You need to know how much delta is. This is the actual signal you have. It has maximum amplitude of 1.5 and minimum minus 1.5. 1.5 minus 1.5 equals 3. Over how many levels? 4. What's the step size? 0.75. Since you have mid-rise, what do? You take the zero. From the zero level, you go above the zero delta over 2, which is 0.375, and below zero also 0.375. So that the distance from here to here becomes equal to delta, which is 0.75. L4, it's given usually from the figure. I give you these are the actual values of the signal: 1.45, 0.75, minus, and it's obvious that you have 4 levels. 4 levels, so that you divide over 4 levels, or I explicitly tell you that L is equal to 4. A quantized sequence, after you approximate them, for example, 1.2. 1.2 is something here. After you quantize it, where do you approximate it? You approximate it to 1.125. So 1.2 is treated as 1.125. How much is the noise error here, quantization error? Is this minus this. There is error. If I ask you how much it is, you just find the difference. And the same you do with the rest. So it's not difficult. Is it clear? This is simple example in where you can design a quantizer circuit. So as I just mentioned, I said there is quantization noise, the way to calculate quantization noise, the actual value minus the quantized value, and you find it. We define it as a Q. A Q is equal M, the message, minus V. The M is the actual message value, V is the quantized value, the difference, delta. Now this is simple, yes, it's not difficult, but if I tell you find the PDF of this quantization noise, then things a little bit turns to be difficult because it requires some knowledge from random signals and random analysis. So in next lecture, we stop here, and in next lecture, we'll explain how to find that PDF of the quantization noise, and how to exactly calculate the number of bits you need to use in order to make the quantization noise below certain level. So thank you very much, and we will continue in next lecture.